teachers, welcome to the last day of your online training program. So today we have a very eminent speaker with us, Shri Anand Kumar. So Mr. Anand Kumar is basically from Vikram Sarabhai Space Center, Thiruvananthapuram. So he is working there since past 3.5 decades. He is an expert in avionics systems and has contributed significantly toward development of various systems of launch vehicles. He has held key positions in his human space flight programs such as group director. Shri Anand is the outstanding scientist grade and currently the deputy director of Vikram Sarabhai Space Center for the management system area. And he is responsible for program planning and evaluation, technology development and management, sponsored research, technology transfer, intellectual property rights and patents, supercomputing facility, computer infrastructure and network, and the campus security, budget, human resources, central library, and space outreach activity. By education, he is MTech in electronics engineering, and he is a very senior scientist engineer in ISRO who has significantly contributed in launch vehicle system. With this brief background of Shri Anand, it's my pleasure and honor to invite you, sir, for your session, and would like to express our thanks to you for sparing your valuable time to deliver the session for school teacher. Now, floor is yours. Over to you, sir.
Thank you, Dr. Harish. So let me first compliment IIRS for conducting such a unique program for school teachers. Actually, the school teachers are the primary focal points which we should be considering in our outreach, because you are the ones who are directly interacting with the next generation of people who are supposed to take India to much greater heights in the space sector. And we look forward to your passing on the message which you have imbibed from these 5 days over to the students, so that they get motivated, because it is very difficult. We do conduct outreach programs for the students, but it's very difficult to reach the majority of the students within the country. But this is a unique program where the teachers with whom the students spend the maximum time in their childhood, so they are being trained and introduced to various topics of the Indian space program, so that you pass on the message to the school children. So with this brief introduction, I'll start my presentation. I'll share my screen from here. If there's an issue, please communicate. Is the screen visible?
Yes, sir. Please go ahead.
Okay, right. So my topic today is primarily on the launch vehicles and the propulsion systems of which ISRO is having, and also our future proposals for the launch vehicle area. Next. So space. You know what space is. I don't have to tell you what space is, but the challenges in space are extreme, in the sense that it is an unforgiving place where the surviving itself is a challenge, because primarily on Earth we are not we are acclimatized to a very favorable environment around us. We have breathing oxygen. We are at 1 bar atmospheric pressure. The temperature is conducive for living. But once you go to space, the situation totally changes. Here you have the advantage of gravity even, where so that helps you to be firmly footed on the ground. Whereas in space, you don't have any protection of that sort, which means it's a very forgiving environment. And so to reach that space, we need to develop technology which have to be developed to address each of the difficulty. A list of the difficulty are just shown here, which majority of you may be aware. We have extreme temperatures. We also have charged particles, and which can cause radiation, which is harmful to not only for a human presence, not only to humans, but also to the electronics in the spacecrafts and the launch vehicles. We have deep vacuum, and there's no oxygen. And then the magnetic fields play a major role, where here on Earth it is very balanced. And of course, the zero gravity, as I mentioned earlier. Coming to the rocket, what is a rocket? Rockets are machines that allow to go to the third dimension. Which is the third dimension? We need to go to an orbit. For placing a satellite in an orbit, we need a launch vehicle. So how is the satellite staying in orbit? If you say that all objects in space also are falling under gravity, it is not that it is being held in space. So what is happening is, if you impart a particular velocity to a body, that will just balance the gravitational pull. It will stay in orbit. So that is how it is orbiting the Earth. That is very clearly mentioned in the, if the velocity is less, you can see the first figure on the left, where the body will fall back to Earth. At the same time, if it is almost there, it will just be on the surface of that, but above in the space, but will not be. But if it is at the right velocity, it will continue to orbit the Earth. So normally, when you say that when anything goes up, it has to come down. That's a universal phenomenon on Earth. But in space, it is not so, because we are giving a proper velocity to the satellite so that it stays in orbit. Next. So we'll start with the basics of rocket flight. So what is the basics of rocket flight? We know that Newton's third law is known to all science teachers. Every action has an equal and opposite reaction. That is exactly the phenomena what is used in rockets also, where the rocket is expelling the hot gas at a very high velocity. So that propels the rocket forward. And how does the rocket respond? It responds by moving in the opposite direction, following the Newton's law, which is pictorially shown on the right side, where the reaction is actually the rocket moving upwards, whereas the action is the expulsion of the gas, hot gas created by burning of propellants at a very high velocity. And coming to rockets and airplane, the question often, that's a clear question which can always arise. What is the difference between a rocket and an airplane? Both are flying in the space. And one thing what I would like to mention is, when we say space, we have something called an imaginary line called the Kármán line, which is at 100 kilometers above the Earth. So anything above 100 kilometers is considered space, whereas anything below 100 kilometers is considered part of our Earth. So primarily, all our aircraft fly at nearly 30,000 to 32,000 feet, which is only about 10 kilometers, whereas rockets travel much higher. And one other major difference is the speed at which, or the velocity at which they're traveling. They travel at nearly 30 to 40 times faster than aircrafts, which means that random to maybe 250 kilometers away, we can reach in nearly 30 seconds. And since the aircraft fly within the atmosphere, even in a car, when we go, we only fill the petrol or the diesel. So for anything to burn, we need oxygen. So how is that there? Because we are on Earth, we get the oxygen from the atmosphere. Whereas in a rocket, we are crossing the atmospheric regime. So we do not have oxygen to support the burning. For that, what we do is, we, along with our fuel, which is called the propellant, we also carry something called oxidizer, which provides the oxygen to support the burning of the propellant. That's one of the major differences between these are two major differences between a rocket and an airplane. And if you see the history and evolution, the basic humans are always, enchanted by the birds flying. So that was how the early men would have thought of how to fly in the sky. Maybe that is how how the Wright brothers invented the airplane. So we started in the 1900s earlier. But even before that, there were the use of rockets against the British by Tipu Sultan. Against the British, he used a cannon with a sword at the end, with a gunpowder, and that was used to attack the targets at a distance. So that was one of the earlier use of, we can say that rocket technology before this 19th century. And if you see the list of people who are instrumental in having popularized or advanced the technology of rocketry, these are the few names which we cannot forget. One is Goddard, then Galileo, Kepler, and Newton. These are the laws which are being used even today for launch vehicles to reach orbit, and not only that, even for satellites and even beyond, even for interplanetary travel like travel to Moon or Mars. we still depend on Kepler's and Newton's laws. And of course, Da Vinci also was a very famous, though he is known for his artistic work, he was equally a very well-known scientist. And also Copernicus and von Braun. Von Braun was a German who was responsible for the V2 rocket at that time of during the Second World War. At that time, Germany had a major upper hand primarily because of the V2 rockets, which the Nazis under Hitler was using, and von Braun was a major lead who took lead in that. And subsequent to that, actually, our current rocket technology derived by the US and USSR are primarily derived from the primary V2 rockets of Germany. And when did the space era start? So this date everybody knows and would be very well etched in the memory of all. The first satellite, artificial man-made object which went to orbit was, or above the carbon line, above 100 kilometers, was a Sputnik 1 by Russia. That was in October 4, 1957. If you see the size and mass, it's a very small satellite. It's 83 kg. We are now talking about satellites of the class of 6 ton, 7 ton. So you can imagine. And it was just a sphere. And it stayed only 92 days in orbit. And it had only a very primitive, if we say now, a radio transmitter which could communicate data to ground. And it was there in orbit for 92 days, and it came back after that. So these are some of the pictures of the first rocket launch made by USSR at the erstwhile USSR in 1957. And then what happened is then the space war started. The USA and USSR went into a competition. It was more of a competition at that time. Who will go first? So again, as you know, beyond then USA also had man-made satellites going. But again, in 1961, Russia again went first by the first manned mission by Yuri Gagarin. But again, that race continued till into the 70s when till Neil Armstrong landed on the moon, and maybe in the early 70s as well. But beyond that, after the end of the Cold War era, it is now not a competition, but now it is a cooperation. And the classical example of cooperation is our International Space Station, which is orbiting as a space lab above the Earth at nearly 400 kilometers. And it is literally an orbiting house, rather, and an orbiting experimental lab, you can say, which is a joint venture by not only USA, USSR. There are many signatories, but primarily it is being maintained by both countries together. And if you see the major milestones which the humanity has achieved in space, and there's no height of achievement than the moon landing by Neil Armstrong, and the classical statement before he set foot on the moon, one small step for man, but one giant leap for mankind. That exactly is true, and that has phenomenally changed the way the space research has been undertaken everywhere in the world. And of course, the very famous statement by our first cosmonaut in space, Rakesh Sharma, when he was asked, how does India look like from the space station? It was DB Salute. It was not International Space Station. There's a space station called DB Salute at that time, which was maintained by Russia. From there, he communicated to the then Prime Minister that how does India look like? When he was asked, he told Sare Jahan Se Acha. So that is another major milestone for India in the international arena of among the spacefaring nations. And then there's a quantum shift when from the conventional satellites and the descending capsules, the USA launched the first reusable vehicle, which was called the Space Shuttle, which took off from the launch pad and which could come back and land autonomously on a runway like an airplane. So this could be used multiple times. So this was an operation. This was the main cargo vehicle to the International Space Station till about 2010, after which it was retired. And that shows that. And the biggest international collaboration is the International Space Station, as I mentioned earlier. But now, currently, the entire spacefaring nations are not on a competitive path, but more on a collaborative path, because there's no point in competing with each other. Space belongs to all. It does not belong to one country. So it is a collaborative effort for all future missions. And now, coming to the Indian space saga, our humble beginnings started in a small church in Trivandrum, Tumba, as shown in the left figure. And this particular place was identified by none other than Vikram Sarabhai, after whom our center is named. So the primary reason why this location was chosen was the magnetic equator passes through this location, and this was conducive to conduct experimental weather studies from this location. So the first Niki Apache rocket was launched from here in Tumba in 1963, and this shows how that was assembled, and we can see none other than our legendary Vikram Sarabhai and Homi Baba addressing reviewing the situation in Trivandrum during the first rocket launch. And the first payloads were tested and carried in bullock carts at that time, and the nose cone was carried, and the parts of rocket was carried on bicycles, and in 1962, and from there we have come a long way where we have reached up to the moon and Mars. And ISRO's life dream was not, we are not competing with them. And Sarabhai had made a very classical statement that we do not compete with any nation on actually whether to go for human spaceflight or whether to go for deep space exploration, but our technologies will be for the benefit of the common man. So that was the motto of and the guiding light for ISRO when it was formed. And from our humble beginnings, from the sounding rocket, which was borrowed and bought from other countries, which was actually a collaborative effort between France, USA, and our USSR. Then we had two-stage rockets imported from Russia, which were went for a long time, and also from France. And then later we had our own satellite, our own sounding rocket, indigenously launched in 1967 from our own soil. And now with that, the real pursuit of science and its use for mankind is shown here. The Earth's magnetic equator, as I mentioned, and this church, St. Mary Magdalene Church, was served as an office and laboratories in the initial era, and now that is preserved and has been converted into a space museum. And coming to launch vehicles, which is the topic of the day, this was a brief history I gave. Now coming to launch vehicles, rocket science is what we need is we have to work with extreme temperature, we have to work with extreme power, we have to work with extreme pressure and at extreme speed. So this shows a typical, the heavy lift, the current heavy lift launch vehicle, which is called the GSLV Mark III, where any propellant when it burns, as you see, there will be a chamber. What is shown in yellow is a chamber where the propellant and oxidizer are mixed and burned. Then we have a convergent, after which the gases are allowed to escape through a nozzle, which will generate something like the power of for a comparison, we generate give the thrust in tons. For comparison, we have just shown in HP compared to a car, maybe with 100 HP, we are talking about 100 horsepower car engine. The thrust, the power which is generated by a rocket is nearly 37 million horsepower. So you can imagine the amount of power which is needed to lift the satellite to orbit. When we say the satellite, we are for launching a 4 to 5 ton satellite, we are having a launch vehicle with propellant something like 450 to 500 ton. So that is the sort of ratio which we have. And if you see the comparison of speed from a car or an aircraft traveling at 800 km per hour, and a launch vehicle at the time of satellite injection is traveling at 2,800 to 2,900 kilometers per hour. And the powers are also shown. There are many pumps in the vehicle to give the fuel, and see that a turbo pump is working at nearly 12,000 kilowatt, whereas an automobile, the car electric motor for the electric cars are to the tune of nearly 100 kilowatt, and even for a train, it is maximum 2,200 kilowatt. So these are sort of power and speed which the rockets have to deliver. And if you see a launch vehicle, it is a multidisciplinary technology. It is not that there is one area which can be utilized for making a launch vehicle. It involves different areas. That is aerodynamics. We are traveling through the atmosphere at a very high speed. And when we cross the speed of sound, we have very critical issues during when the vehicle crosses the speed of sound. So we have to tune the ascent trajectory is tuned so that the loads on the vehicle are less. Otherwise, we'll have to make very huge structures for which the mass of the vehicle will go up. So that has to be very critically assessed and done. So for that, we have a separate aerodynamics and a structural design team available who specialize in that area. And then what is called the mission design is what I told. We have to clearly say which is the optimum path to go to orbit. So that is very clearly addressed by doing various simulations. And then we have something like what is called a closed loop guidance and control. What is guidance is, we have three elements called navigation, guidance, and control. What is meant by navigation is, you know, when you want to go from point A to B, if you know the path, you know how to go. If you're driving a car, you know from the next junction, you have to turn left, then go right, etc. But a rocket is going on its own. It has got a computer on its own, but it does not know where it is. So for that, we have got a navigation system which comprises of gyros and gyroscopes and accelerometers, and which are aided by our own indigenous positioning systems. So that will tell you where the vehicle is. Navigation tells you where you are or where the vehicle is. And guidance, what is guidance is, our endpoint is known. We know that where in orbit we want to reach. So guidance is an algorithm which computes on board by itself, which is the optimum path to reach from the present point to your final destination, which is the optimum path which saves fuel, which reduces the load on the vehicle, and which is the optimum path to go there. So that is provided by the guidance, which are algorithms which are developed in-house, and that is residing in the launch vehicle computer. And control is actually, the real control is something like the actuators, like your accelerator and the brake of the car, where you, or the steering, where you turn, when you turn, the steering changes, the car changes direction. The controls are actuators which actually move the nozzle to either direction, in all three directions possible. It is possible, so that by moving the nozzle, by deflecting the flame, the vehicle can be tilted. So that is the role of control. And we have to work with a host of special materials and chemicals. All special materials, because we are, as mentioned earlier, we are working with extreme temperatures, extreme harsh conditions. So different sort of exotic materials and chemicals are to develop. That also is being that also is done in-house, and which is also transferred to industry later. And we have fabrication, very critical fabrications, because in a vehicle, if you have a turbo pump, the tolerances are of the order of microns, not even or nanometers, it's in microns. So we need fabrication, cutting edge technologies for fabrication involving advanced CNC machines, etc. And of course, the propulsion systems have to be there to propel the vehicle. And avionics or software, the brain of the vehicle, which though it constitutes a very small element, but during the entire flight of the vehicle, it is being controlled by the electronics and the associated software associated with it. We also have a space ordnance system. What is meant by ordnance is, ordnance is something called like an explosive device. But here we have tamed that explosive system so that for each the ignition of the motor to happen, we need a spark, like a spark plug of the car. We need a spark to be there to ignite. So that is provided by the ordnance systems. Similarly, we don't go at one shot to orbit. We stage and go, in the sense that once the first, because it is not practical to build a big vehicle with a single stage to take to entire vehicle to orbit, which is not an efficient way of doing it. So we have split the entire velocity addition into different stages. So if you see after the first stage performance is over, we have to separate that, and then the next stage is ignited. So this allows an optimum payload delivery to orbit. So for that, even for separation, we need what is called as pyrotechnic devices, which are activated by ordnance systems. And of course, the entire vehicle is like a 15-16 story building that has to be built up at the launch pad, and that is done by the vehicle integration and the checkout team. And the entire thing has to be entirely simulated end to end. For that, we need detailed mission simulations, including we have angular motion simulators which can simulate the movement of the vehicle, and that is done in-house. We have a mission simulation lab for doing it. And since, as we told earlier, the vehicle has to go through different varied environments, very harsh environments, we have to test it before we go. And our policy is test as you fly and fly as you test. So we test everything in the flight condition and ensure that nothing is left untouched and nothing is addressed, so that we don't face any surprise during the flight. And of course, for anything to work successfully, we have to have a very highly reliable vehicle, and that is ensured by a quality and reliability engineering team, which goes through each and every aspect of the vehicle and certifies that the vehicle is ready for flight. Next. And as I told earlier, the major elements in a rocket system are, if we start from the bottom, we have the propulsion, which is nothing but the foot of the vehicle, and which releases it's an energy releasing system, converting the potential energy to kinetic energy. Basically, as you know, energy cannot be created or destroyed, so we are not creating an energy here. The potential energy is being converted to kinetic energy as the vehicle moves forward, and the control, as I mentioned earlier, as are like the limbs, and the avionics is the brain. The structure is the shell, which provides the navigation and guidance are the eyes, and the telemetry. What is meant by telemetry is we have an entire system going up, and we need to know what is happening to the vehicle at any point of time. So we have got multiple measurements which are being measured, like where you want to know what is the velocity at which the vehicle is going. We want to know what is the pressure it experiences, whether the temperatures are okay. So we will measure all these parameters in the launch area, but we have to get it in the ground. How do we get it? We have got on board our own telemetry transmitters, which transmit the data to ground and which are acquired by the ground. We have got our own ground stations which acquire the data in ground and which is later used for analysis after the flight. And the Spyros, as I mentioned earlier, they are high energy systems which can trigger on-board mechanisms through sudden discharge capacity. Next. And coming to the propulsion system, as I mentioned, it's a rocket foot. There are primarily two types of propulsion systems. Propulsion system which ISRO is utilizing. One is a solid propellant and another liquid propellant. Coming to liquid propellant has got a liquid fuel and a liquid oxidizer. So both are stored in separate tanks, and from these tanks they are pumped to what is known as a combustion chamber. And there are types of propellant which are called hypergolic, which means when they come into contact itself, they ignite. So we are using such propellant and oxidizer mix, so that though they are stored separately, once they are pumped by our pumps to the combustion chamber, when it comes to a combustion chamber, when they come into contact with each other itself, it ignites. And the burned fuel, the hot gas is expelled through the nozzle, and that gives a thrust for the vehicle to go forward. So as you can see here, we are carrying both fuel and oxidizer. Similarly, in a solid propellant, it is a solid fuel which we are using. And solid fuel has also got a solid fuel and oxidizer mix is kept inside what is known as a motor case. And that motor case consists of what we call something called an igniter. So what will happen is the igniter provides a spark like the spark plug of the car, so that once the spark is given, this fuel oxidizer mix gets ignited, and again the entire propellant gets consumed and burned. And in the same philosophy like a liquid engine, as I mentioned earlier, it is expelled through the nozzle, which gives a necessary thrust. This on the right side, you can see the complex motor case, which is a tray ricotta. This is one segment of the motor case. Similarly, there are multiple segments which are joined together, and then the solid propellant is mixed and poured into it, and it solidifies and is used. And these are the NASA pictures of some of the propellant tanks which they are using. And our own liquid engine is shown on the right side, which is called a Vikas engine. And that's a very compact liquid engine which we use for our second stage of our PSLV and GSLV. And what the earlier I showed staging. Why we need a staging is we need, as I told you, we cannot go to orbit in single shot. So what this shows a typical exploded view of GSLV Mark II launch vehicle. We have the first stage, and we have got 4 strap-ons, and then we have the second stage. They are all connected through separate stages called interstages. When 2 stages have been connected, so we connected using a small structure called an interstage, so that the primary reason is the stage above will have a nozzle that should not go and hit the bottom stage. So to accommodate the nozzle, we provide a small interstage. So that is there in everywhere, whether in between first and second, and between second and third. And on top of that, on top of third stage, we have got something called an equipment bay, which I mentioned houses all the entire electronics and the avionics and the software, which controls the entire vehicle during the flight. And then above the equipment bay is our primary area of focus, which we call the satellite has to be positioned there. For that, we have an adapter, which is called a payload adapter, over which the satellite is assembled. And to protect the satellite, we have got something called a payload fairing. Primary, the use of a payload fairing is when they are going through the atmosphere, satellite has got very sensitive components. So they have to be protected till the 100-kilometer height is achieved. We have got a dense atmosphere, getting rarefied as we go up. So when the vehicle is moving at a very high speed, the heat generator will also go up. So we want to protect the satellite, and for that we are providing something called a payload fairing, which will protect like a cocoon. The satellite will be cocooned inside that, and once we cross the atmosphere, this payload fairing will separate, and then later when we reach the orbit, the satellite also gets separated. And if we see the total the percentage of mass which goes into the entire vehicle, when I say the total vehicle is something like 500 ton, we can see the propellant constitute 90% of the mass, and 10% is for structures and avionics, and the actual satellite will be something like 0.5 to 1%. And staging, why I told earlier is why we need staging. Staging always increases the efficiency of that vehicle. So this shows a typical NASA. Is there a video? No. Okay. This shows a typical NASA space launch system, and on the right side we have got the GSLV Mark II, which shows that the first stage is comprised of a main solid core and surrounded by 4 liquid strap-ons, which are primarily meant to take the ascent vehicle up. And then if it is a GSLV Mark II, the second stage is a liquid stage. This will come above the first stage, and the third stage is a cryo stage, which will come above or even on top of the second stage. These are 3 stages of a typical GSLV Mark II launch vehicle. And as I mentioned earlier, the vehicle has to be built up at Sriharikota. We have got a massive assembly tower sitting at Sriharikota, where the 15-story vehicle has to be built. So what we are doing is we are assembling in stages. As you see, there's a huge crane on the picture 1, which is lifting the solid motor segment onto the pedestal. And over we have got 5 segments of the solid stage. They will be assembled and they will be joined together. And then the strap-on motors will be assembled. That is shown in slide picture number 2 and 3, where 3 means all strap-ons are completed. And when you see picture number 4, we are seeing the second stage, which is being lowered onto the first stage, into the inner stage. And on picture number 5, we are seeing the PS4 and the EB being lowered. And on the picture 6, you can see the equipment bay sitting there. The avionics can be seen, and the satellite is being assembled on top of the vehicle. After which it will be covered by the satellite is integrated now. After that, picture number 8 shows how the payload fairing looks like, and it will be covered. Satellite will be covered, and then the vehicle will be moved to launch pad at picture number 10, and then we are ready to go. It is months of hard work, and 20 seconds we achieve the launch, and we are in orbit. Then when the vehicle goes up, we need to track the vehicle. How do we track the vehicle? We have got ground stations sitting across the country, and even at Port Blair and at other areas outside India to track our vehicles as we go to orbit, because we have got different orbits. Once, as you know, there are geostationary satellites which are 36,000 kilometers. For that, we have to position the satellite near the equator, so above the equator. And we also have Earth observation satellite which actually the satellites moves from pole to pole, which you would have heard from our satellite team when they presented. So we have got different routes through which the launch vehicle delivers the satellite. So to track the launch vehicle, we have got ground stations with the dish antenna shown, which to which the vehicle transmits the data acquired on board, because it has got its own intelligence. It transmits to ground station, and through which a different set of radars, we track the vehicle as it goes up. And our spaceport is known as Sriharikota, which is the Satish Dhawan Space Center. That's India's spaceport, and that is located on the east coast of India in the Bay of Bengal. As I told earlier, we have got 2 launch possibilities. One is a geotransfer orbit, when you want to launch a geostationary satellite. That will be going to near zero inclination, which is go above the equator, and the sun synchronous orbit or the Earth observation satellite will go to the pole, so the satellite rotates from pole to pole. And why the advantage of SHAR is, the SHAR is comparatively close to equator. It's only 9 degree or 10 degree above equator, and we always have an eastward launch. Why eastward launch is, as you know, Earth rotates from west to east. So the advantage of the rotation of the Earth also can be given to the launch vehicle. It gives an additional velocity. Otherwise, if you are launching from the west to east, we need additional propellant to overcome this rotational force also. Now, this also adds to the velocity. So actually, there is an added advantage for having an eastward launch from SHAR. And another point is being such a, as you know, as we have mentioned, there are huge quantities of propellant available in the vehicle. And so this should not be a safety concern to the ground personnel and to the inhabitants. So we have chosen an uninhabited landmass and very close to sea, and always our trajectories are overseas, so that even in case of any mishap, loss of life is not there at all. And this shows a picture of the vehicle assembly building. As I mentioned earlier, you can see the vehicle coming out of the vehicle assembly building, and vehicle assembly building is also so massive that the entire vehicle can be assembled inside the vehicle assembly building. And on the next picture, you can see the vehicle majestically sitting on the launch pad. And on the four structures, what you see are the lightning protectors. Because the vehicle is standing tall, we need to protect it against the lightning. So we have got huge lightning towers, protection towers around the vehicle, so that vehicle is protected. We have got two launch pads at Shri. One is called the first launch pad and second launch pad. The first launch pad is shown on the right side, and the second launch pad is shown on the middle picture. And the control center for the launch vehicle, as we progress towards the launch and the countdown, we need to monitor the vehicle at a distance, because we cannot be very near the vehicle with such a high quantity of propellant there. So we have got a launch control center again in Shri, located at a distance of nearly 78 kilometers away from the launch pad. So you can imagine, even at this location, we can hear the reverberation as the vehicle lifts up. So this is the brain at SHAR, which controls the vehicle during the pre-launch operations and also tracks the vehicle after the liftoff. And if you see the history of ISRO's launch vehicle, we talked about the RSR sounding rockets earlier, which were small pencil rockets which we launched from our Tumba Equatorial Rocket Launching Station, which used to go up to 65 to maybe 70 kilometers, but that never goes to orbit. Actually, it is only like a projectile. It goes up, does a study, and then it falls down. During the fall down, some shaft is released and which are tracked and being monitored for atmospheric studies. But our first attempt to launch a satellite into orbit was SLV-3, whose product director was none other than the great Dr. APJ Abdul Kalam. And we had very humble beginnings. We started with the liftoff weight of the SLV-3 was only 17 ton. 17 ton, and it was an all solid vehicle, and it had only a payload or a satellite of only 40 kg. It carried a payload of 40 kg. As you progress, you will see to what level we have come from our humble beginnings in 1980 when we launched the first satellite. We augmented the SLV-3 with two strap-ons around that, and we could achieve something like 150 kg to orbit, a slight enhancement. But our quantum jump came in PSLV when a host of new technologies were tried out, and PSLV was a quantum jump from the 150 kg to nearly 1,900 to 2,000 kg payloads this had, and from the all solid configuration to we developed our own liquid engines as well, and it also had the first closed loop guidance and control implemented in PSLV, whereas in ASLV the guidance was all open loop where the trajectory was pre-fed. So it followed a trajectory which was decided a priori, whereas in PSLV onwards we are deciding on how the optimum path to go to orbit. And GSLV was an improvement upon PSLV, where we mastered our own cryogenic technology and inducted the cryogenic engine into GSLV, and that is the vehicle which flew the first cryogenic engine as upper stage, and from there we could go up to 2,200 to 2,300 to a geostationary transfer orbit. Whereas the next vehicle, which is called the Bahubali, which is our heaviest launch vehicle right now, is the launch vehicle Mark III, or what is called GSLV Mark III, which is a very simple vehicle, but it is huge, and it has got three stages: solid, liquid, and cryogenic. with a lift-off mass of 640 ton. So you can see the quantum jump from 80 to nearly 2014. We had migrated from 17 ton to 640 ton, and the payload also, the satellite capability also increased from 40 kg to 4,000 kg, which is 100 times. And then parallelly, ISRO also worked on a new vehicle. It's a small vehicle called a small satellite launch vehicle. This is an on-demand, considering the huge demand globally. This vehicle was conceived and developed within Vikram Sarabhai Space Center, which is a small all-solid vehicle with a last-stage liquid engine to precisely achieve the orbit. This could carry a payload of 500 kg to 500 km circular orbit because there's a huge demand globally for this. This is a very quick turnaround vehicle. We can, once all stages are made ready, we can launch the vehicle within 3 to 4 days from Sriharikota, where the other vehicles require more than a month of preparation at Sriharikota. So this is an on-demand launch vehicle which was developed by ISRO, which is the newest vehicle added to the stable. Though it is a small vehicle, but it has got huge commercial applications. And coming to how big they are, when I told about the height and the diameter, height and the weight, for a comparison, we are saying a 12-story building scale. On a scale is shown a 12-story building, and the weight with a vis-a-vis a car, as well as the payload is also compared across this. So this will show you the comparison between SLV3 up to GSLV Mark 3 in terms of height, weight, and payload. And as you know, this would have been covered probably, but I'll just brief on what is the satellite. Satellite, we have got two types of satellite. As you know, what's a natural satellite is something, all heavenly bodies. The moon is a natural satellite of the Earth. Similarly for Jupiter, and all other satellites have got its own natural satellites. They also are orbiting their respective mother planet. How is that? They are held in force by the gravitational pull of that mother planet, and it is also rotating around the Earth in the same way with a proper velocity, so that it does not fall into the Earth or it does not fly away. Similarly, an artificial satellite are also put into orbit with the same philosophy, that you should revolve around the planet and other bodies. And the purpose, and why do we launch satellites? That would have been covered in 2 sessions, but primarily our primary objectives are communication, remote sensing, navigation, and other scientific exploration. And major elements in this slide I will skip, because I heard Shankaran sir has already given a talk on the elements in a satellite. So this slide I will skip. And a brief history of satellites launched in our own launch vehicles. If we see, the first satellite made in India was the Aryabhatta, and from 1975. So 50th anniversary of Aryabhatta was celebrated recently. From there we migrated to the Bhaskara, Rohini, Apple, and now as we grew in 2023, as recent as 2023, we had the Aditya L1, which was also covered earlier. And before that, the historic moon landing with the Chandrayaan-3 mission also had taken place. Satellites application, they are rise in space, primarily used for remote sensing, communication, navigation, scientific missions, and futuristic applications. And now the major thrust for ISRO also is, we are also trying to, as our space vision has been outlined by the government of India, we have been envisioned with a vision of having our own space station by 2035. This is very similar to international. For that, I'm just giving a background of the space station. The space station is a multinational collaborative project which involves five countries, and the space station is now at a height of 420 kilometers above the Earth, and it is orbiting at a speed of 7.66 kilometers per second. And it completes a revolution around the Earth in 92.68 minutes and orbits Earth 16 times in a day. Okay. And the satellites in the international arena, I'll just highlight the satellites which are from the first Sputnik. Now we are talking about space stations, then Crew Dragon, which is a space capsule which goes to the International Space Station from USA, and we are there are also lunar gateways. There are intermediate gateways which will be used as an intermediate point for going to moon and coming back instead of having directly going to moon. And space is the ground for limitless application, and satellite constellations are for communication. Next. And space telescopes are the major one. We also had our own look at the space with an astrosat earlier, and now, as you all know, we have the Hubble telescope sitting there, which has been repaired recently. And as we grow, as we go forward, we will have bigger space stations and bigger telescopes as human endeavor is to explore space. And protecting Earth from asteroids is another main aim which is being projected. There are mechanisms for doing it, which is being explored, like diverting the asteroid with a hit. And also now space tourism, like we go to tourist places, space tourism is getting common. There are already vehicles which are available in the United States, which take us to like the Blue Origin and Shepherd, which takes us to 100 kilometers, and you can enjoy the microgravity experience as we come back. And also even they are proposing as a tourist to space station. And in the future, we are going to have lunar and Martian gateways, which will be like a big house in the space where you transport and travel, stay there for a few days, and from there you can go to Moon, Mars, and then come back. And coming to ISRO's prestigious program, the next program on the anvil is the Gaganyaan. As you know, as Gaganyaan, the name implies, it is taking humans to space and returning them safely back to a predefined destination on Earth. So we are using our GSLV Mark III as the vehicle to take a crew module with a servo. What is called a crew module is a crew module is the living quarters of the crew. We take them to orbit. It will have its own life support system, its own power generation system. The life support system will ensure that we are the crew is in a condition as on Earth with the adequate oxygen in the same condition as on Earth with 22% partial pressure of oxygen, the same condition, and the temperature is also less than 25 degrees as in an air-conditioned room. So that will be maintained. These are the challenges in human spaceflight. As we go forward, then this shows a typical mission. Can you just go back? So it will be taken to a low Earth orbit. It'll be staying in orbit for 3 to 4 days. After which astronauts can do experiments. After which we will ensure that the Gaganyaan module is reoriented. We have to do, since we are in orbit, we have to decrease the velocity if we have to come back. So we decrease the velocity using appropriate propulsion system, and then when the crew module descends, it will be encountering the atmosphere. That atmosphere itself will be reducing the velocity due to aerobraking. This phenomenon is called aerobraking, but it will generate a lot of heat. So this heat, for protecting the heat, we have got robust thermal protection system, which will protect the internal capsule from heat, which means that though the outside temperatures can touch up to 2000 degrees Celsius, the internal temperature will be less than 30 degrees centigrade. So, and crew module will come down and land safely using parachutes and deceleration systems on sea. And this is the crew has to be saved in the ascent phase. When the vehicle is going up, even if there's any issue, the crew has to be properly saved. For that, we have got a robust escape system which will save the crew in case of any exigency during the ascent phase. Next. And Gaganyaan, we have got many critical technologies. The food of astronauts are to be like in Earth. We have got a Defense Food Research Institute at Mysore, which is developing the space food. We need simulators to simulate the crew management conditions in orbit. We have to develop the escape systems. We have to do recovery logistics. Then the recovery and the parachute systems to reduce the velocity. And we need communication infrastructure and network to communicate with the crew module, and we need an extensive suite of astronaut training and flight suit to protect the crew in case of any emergency. And next, what we have on the project on the anvil is a reusable launch vehicle. We are also trying to demonstrate a reusable launch vehicle like the space shuttle, where it can take off from a launch pad and come back and land on a runway. So, that is also our next philosophy. And velocity reduction techniques, apart from parachutes, we are also working on aerodynamic decelerators, which can reduce the velocity. These are all cutting-edge technologies which ISRO is now working on. And there's a vision for India's reusable launch vehicle. As you see, we had tested one reusable launch vehicle landing on a runway, which when it was dropped from a 4-kilometer altitude, that picture is shown on the left side. So first, it will be taken on an Air Force helicopter and dropped, and it will land on a runway. After that, we are trying to demonstrate by taking it to orbit and landing on an identified runway. These are the roadmap which we have envisaged for our reusable launch vehicle program. And from our humble beginnings in Space Museum at Tumba to sounding rockets. Next. And this is our Space Museum, and which is open to visitors also. We have come a long way, as I mentioned earlier, from the humble beginnings at Tumba to the position where we are. Thank you.
Thank you, sir. So thank you for your session, sir. It was really wonderful. And we received few questions from participants. If you permit, we can take it, sir.
Thank IIRS for inviting me to deliver this important lecture to the teachers, as I told earlier, who are going to be ISRO's ambassadors to the younger generation, who are going to take ISRO forward.
Yes, sir. Thank you, sir. Sir, we are getting many questions from the teachers, although time may not permit us to take all the
I
questions.
have another meeting scheduled at 12. Already a call has come. Maybe I can take a quick 2 or 3 questions.
Yes, well, yeah, only two questions I will take, sir. So one question is coming that a very interesting question. Can we think about to develop a fuel which doesn't require oxidizers?
There is no fuel which does not desire an oxygen, because if you want to light a matchstick, you need oxygen. For anything to burn, oxygen is a must. Even for quenching a fire on a ground water, instead of spraying water, the best thing is to cut the oxygen. So without oxygen, we cannot have fuel burning. So oxidizer is a must. But as a corollary to the question, I will answer one more point. There are experiments which we are experimenting, which are called air breathing propulsion system, where we are trying to take in oxygen as we go up. Anyway, we cannot avoid going without oxygen for burning. So as we go up the atmospheric regime till 100 kilometers, if we have a mechanism of taking in oxygen and storing it, for beyond that, we can use that oxygen for burning the propellant instead of using carrying an oxidizer till the end. Actually, this is a very preliminary stage of development which ISRO has taken, and we have demonstrated that for a few seconds in one of our earlier flights very recently. And we have technology development programs lined up for demonstrating a long duration flight of nearly 250 seconds with an air breathing propulsion. And that will be, if once that comes through, that will be a game changer in not only in launch vehicle, even in traveling from one place to another. Instead of an aircraft, we can call something like a hyperplane, which we can use, which can travel from Trivandrum to Bangalore in a few seconds. So that is being experimented worldwide by research is going on worldwide in this area, and ISRO is also not behind. We are also working on the same technology.
Great, sir. Thank you. Sir, one more question I will take, sir. This question is, there are two type of fuel. One is a solid and liquid. So why liquid is more used in the rocket system? This is the question.
We have got something called the efficiency, like our fuel efficiency of a car. We have got something called an ISP, which is called specific impulse. Specific impulse is actually a number which denotes how much more efficient the propellant is, how much more velocity this can add. Compared to a solid, liquid engine has got this specific impulse, higher specific impulse, and Cryo has got even higher specific impulse. So, but solid motors are quick acting and they give higher thrust very quickly. So that is why if you see all our lifting, for the first stage is starting with solid, but as we go up, we use liquid and cryogenic technology primarily to take leverage of this higher specific impulse, and that will be like a higher fuel efficiency, so that it gives higher velocity for the same quantity of propellant we are carrying.
Yeah, thank you. Thank you, sir. There are many questions, and very interesting. This is a lot of appreciation about your session. They are telling it was really wonderful and very informative session. And one last question I will take for discussion here. So as you mentioned in your presentation that ISRO is already working in the reusable launch vehicles. So the participant would like to know what is the status. Are we going to launch a satellite using the reusable launch vehicle in future?
Yeah, I'll tell you, we have got a reusable launch vehicle program. As part of that, we have developed for the past 2 years, we have been working on that. And we have developed a reusable winged body, which was shown in the figure there. And actually, we had taken it, our Air Force team had supported and taken it to a height of nearly 5 kilometers. And it was dropped from the helicopter, and it autonomously, without any control from the ground, or there's no pilot, of course, inside, with no control from the ground, it automatically maneuvered its way and landed on the runway just like an aircraft and came to a stop. And since the landing velocities of such reusable launch vehicles are of the order of more than 300 and more than 300 kilometers per hour, which is at least 1.5 times more than the landing speed of a commercial aircraft. So it is even higher than that's a real challenge. It's much higher even than a fighter aircraft landing speed. So that technology we have demonstrated through 3 landing experiments where we did not go to orbit, but the landing aircraft was dropped. I mean, this winged body was dropped from a 4-kilometer height. But we are working on a reusable launch vehicle which will be taken atop a GSLV modified GSLV rocket, and which will go to a 300-kilometer orbit, which is supposed to deliver some payload there. It is supposed to be in orbit for a few days, and after that, we are planning to return it. It will land like a space shuttle on a runway. So that work we are going on. Maybe in another 2-3 years' time, you will see our own reusable launch vehicle landing on a runway.
Yeah, very good, sir. Thank you. Sir, with this, I'm going to close this session now because you are also busy. And
Yeah,
thank you very
thank you.
much, sir, for sparing your valuable time. It was really wonderful session, and participants are, of course, appreciating it. And thank you very much. And we would like to have your permission to host this particular session in YouTube channel as well.
Thank you very much.
Thank you, sir.
Thank you. Okay. Right.